Thank you. So yes, I named named the Python module. I'm going to talk about the Irish Earth Observation module. It originally was not named that. It was there's some history behind it, and currently it only supports Landsat. Well, what is it? First of all, it's open source, and it's on GitHub. It maintains a local remote sensing image data library for Ireland, specifically at the moment only Landsat 4 through 8. But Sentinel support is going to be added very soon, partly because I need to ingest these data into my own system, and so I'm going to have to go ahead and write the code to get it into a useful format for myself. Some history behind the module. It began several years ago, I would say even like 10 years ago at this point, as a set of Python scripts to do a number of functions, specifically maintain a library of in-house data, perform cloud and shadow masking where was needed, identify, process, and compare scenes for similar days of year, that is, plus minus 7 days from different times of the year. I used to work for the USDA Foreign Ag Service as a contractor, and we would frequently have to compare crop conditions in various countries using remote sensing data. And so we would be comparing Landsat imagery or AWIFs or something else from one year, and then see how does it compare to the previous year or to an ideal year or even to an average of several years. And so I needed software to go ahead and maintain that, because doing it manually was just a pain. At the time, I was working primarily with ArcGIS and Envy, so a lot of these were based on those and around the Python modules that interface between those softwares and each other. In fact, you need to use, at the time, I don't know if that's still the case because I no longer use either, but at the time you needed to go ahead and use Python to interface between ArcGIS and Envy. Now, my work changed. And additionally, ready-made surface reflectance products became available from the USGS ERA's Data Archive Center. The specific algorithms they use are called LEADAPS or LASRC. LEADAPS is for Landsats 4 through 7. LASRC would be from Landsat 8 and 9 would be using those. 9 hasn't been launched yet, but it's in the works. And so various products also became available, so I had to go ahead and make this. Now, make some changes. Now, I also decided that I was going to move away from proprietary software, partly because I moved from the USDA, which was relatively well-funded, and we had lots of proprietary software, to Chagos, where things were not as well-funded. And while we had ArcGIS, I was the only person in the organization who had Envy. So if I needed to get a new computer or move or whatever, it was a pain. So I decided, okay, I'll go open source. Use instead GDAL and NumPy. And in any case, it turns out that ArcGIS and Envy, etc., they're all calling GDAL anyway. So better to directly access it. The other thing was I was working with data from different scales, etc., and I found that if I used things like NumPy, I had more control over the data than I would if I was just using some proprietary software. So, in general, my work has revolved around processing very large data sets. I started out as a crop condition analyst for the Middle East, specifically Syria, then Iraq, Iran, Afghanistan. I moved on to looking at other parts of the world, including Europe, Southeast Asia, the United States, even, and that was for a group known as the International Production Assessment Division, or IPAD. IPAD was called IPAD before there was such a thing as an iPad. And what they do is they track global crop production. The U.S. Department of Agriculture is a civilian agency. And what they want to know is what's happening with major grains, oilseeds, and cotton. They want to know what's going to happen with the prices, etc., because at the end of the day, nobody is happy when suddenly overnight the price of wheat triples. This did actually happen. It was in 1972. It was an event known as the Great Grain Robbery. And I'll tell you that story right now. In 1972, the Soviet Union was experiencing massive crop failures with its wheat crop. Well, the USDA has what are referred to as crop attaches, and they go around and they check on the agriculture in each individual country. Well, not every country, but a lot of them. So there's one that was in the Soviet Union, now currently would be in Russia and the former Soviet Union. And of course, they do this crop travel in conjunction with local governments because, let's face it, countries don't like it when foreign agents are going around, checking on things without their approval. So they take they knew they were having crop failures. They took the USDA crop attaché to areas they knew were doing very well. He reports back to Washington, the Soviet crops are doing great. In the meantime, they somehow talked the U.S. government into selling them a quarter of the U.S. wheat crop and somehow even managed to get the U.S. government to subsidize us. Well, when everything was said and done, suddenly they discovered that no, the Soviet wheat crop wasn't great. In fact, they had massive crop failures, and overnight the price of wheat triples. And of course, that meant the price of bread had a very sharp increase, and nobody was happy. 1972 also happens to be the year that the first Landsat was launched. And suddenly they're like, oh, we have an Earth remote sensing satellite that we can use for civilian purposes, which isn't subject to any serious security or anything like that, so we can publish the results. And that's where a lot of the agricultural remote sensing begins. Back in 1972, incidentally also the year I was born. So moving on, I then came here 6 years ago for what was referred to as a C4EP project, which was to look at land cover and land use in Irish forests. The results you can see up there, that's just a case where we were looking at forest cover change, and you can see different types of change that were occurring, cases where there was deforestation, where there wasn't, where there was afforestation, of various areas. That's for the Ballyhora Mountains. And then on the image on the right would be the year of the last detected change. And that was all done using Landsat data. So big data analyses require uniform processing. And so I created IEO as the backbone for my data processing routines. The specific module, specific software that does these calculations calls IEO into it. It's a different software called i40o, which is also on GitHub but hasn't been published yet because we haven't published the paper yet on it. But it is a land cover change module which uses IEO for calling data and for also for writing, etc. So frequently I found that that when using other people's software, they didn't necessarily handle the data that I wanted to, particularly if I was getting it from the USGS. For example, they will process the data and they will even process it to NV format, but it doesn't have a lot of information in there that I personally think should be there. For example, you get all the data are presented in separate bands. So band 1 will be in a TIFF or a GeoTIFF or an NV file. That's band 1, band 2, band 3, but it doesn't have in it the band names. So if you're talking about Landsat 7, it's Landsat 4 through 7, it would be the blue band. If it's Landsat 8, it's a coastal aerosol band. It doesn't have the wavelength information, including various parameters like the half width, or the full width half maximum data, etc. It was also missing temporal data. So, for example, what day was it acquired? And then there were other data. There were some other issues, for example, and I'll discuss this in a later slide. Projections, things like the data come in UTM, and really here in Ireland, it's best to work in Irish Transverse Mercator as opposed to Universal Transverse Mercator. I'll discuss that a little bit later. The other thing is, there frequently a lot of the products were missing classification or output data. For example, if it was a classified data set, there used to be a product called FMask, and there were 5 basic classes to it, and unless you knew what you were looking at, unless you knew what the numbers were, you couldn't get anything useful about it. So there's a very coarse classification for clear land, clear water, snow, ice, cloud, and cloud shadow. And so basically I went ahead, added in things like, for example, class colors and labeling and all that, so that it would be easy for anybody just to pull that in on ArcGIS or whatever software they're using and at least know what they're looking at without having to jump through hoops. The other thing is that when you're doing a lot of processing, you want to know where the parent data sets are, particularly if you discover there's a problem with your data. I discovered, for example, that a lot of Landsat imagery that was supposed to be properly geo-referenced was not, in fact. And in some cases, pixels were up to, sometimes could be 100 meters off, sometimes over a kilometer off, and so on and so forth. And so using this allowed me to go ahead, identify the problematic data sets, remove them. In fact, there's actually one thing which I forgot to put in a slide on it, but there's a list of dates which are known to be problematic. And so you can actually go ahead, call in that list, and say, okay, I don't want to include any imagery from those dates because those are known to have some sort of quality issue. So why use the Irish Transverse Mercator projection? First of all, it's optimized for the island of Ireland and GPS. It's used by the Ordnance Surveys of both the Republic of Ireland and Northern Ireland. So basically, if your application is specific to the island, you should be using Irish Transverse Mercator. And definitely not Irish National Grid. That needs to go away. There are issues with that, and people need to stop using it. I know people love it, but it's time for it to die. So why not keep data in Universal Transverse Mercator? I mean, it's used for Landsat, it's used for Sentinel-2, it's used globally. There are some issues, software issues, which I think a lot of them are now being addressed in software, but still, I discovered that misprojections along zone boundaries are possible. And this occurs because the border between UTM zone 29 north and 30 north happens to be just to the east of Dublin. And that's also where some of the scene centers are exactly located. And when that happens, you sometimes get misprojections on these boundaries. For example, we can see there that a scene that was supposed to be over right over the 29-30 boundary is in fact misprojected over the 28-29 boundary. Partly because most of the imagery was for UTM zone 29, and that one happened to fall into 30, but the software didn't properly handle that. I was talking with people at a conference a number of years ago, and they're like, "Yeah, we have this problem too." And of course, they weren't in Ireland; they were working elsewhere in the world. So the other issue is that at higher latitudes you get distortions, particularly, and then the other thing is if you get close to the poles, then some of those areas have their own projection issues. But I'm not going to get into that. So yeah. So basically, I went ahead and created this. One of the functions it does is it moves everything from UTM to ITM, and that solved any problems I had. So what else does it do? Well, first of all, it saves image library metadata in a geo package later. It used to be a shapefile, and then I decided that I was sick and tired of having to track several different files just to have one layer. So better to use GeoPackage because that's just one file and you can stuff multiple layers in them. So it downloads the footprints and metadata for all available scenes from the USGS. As of a few days ago, it was over 13,000 just for Ireland. This includes ingested data sets. It allows the creation of processing lists for the USGS EROS ESPA architecture. ESPA is the Earth Sciences Production Architecture. I forget what ESPA specifically means, but basically you get a list of product IDs, you upload it to the server. Currently it's a bit of it's not exactly ideal. I'm going to incorporate some more, I'm going to incorporate the ESPA API so that a script can just handle this rather than having to go ahead, save a file, and then go ahead and manually upload it to ESPA, and then have them process it. But once everything's processed and downloaded, and I do use ESPA software for the downloading part, it then goes ahead, ingests these, brings it into Irish Transverse Mercator. This includes also creation of cloud mask NDVI and EVI data. It also performs cloud masking on the actual data sets itself so that if there's a completely cloudy part of the scene, those data are not saved to disk. Among other things, just to give you an idea, this is what the CatalogGeo package looks like. And if you see, like on the 7th, on the previous side, there were actually 15 fewer scenes available than there were on the 11th when I last checked the database. And I'll actually check it later today. Maybe there's some new images, maybe there's not. But to give you an idea, it saves the metadata into a table along with the footprint. That's actually not what the footprints. These, by the way, are idealized footprints. Those are not what the footprints really look like. That's more of a mess. I also created what's referred to as the All Ireland raster tiles, and the reason why is because you end up with a lot of data that you've downloaded from GeoSGS, and it's either over the ocean, and my applications are for land, so I'm generally not interested in what the Irish Sea looks like. Or the Atlantic or whatever. So I created this, basically created this grid that included all the land tiles, and so it doesn't save data that are not on the tile. It also eliminates anything that's completely either cloud or cloud shadow. And so that's one way to cut down on the amount of data that I actually need to save to disk. Currently, it only handles WRS2, which is Landsat 4 through 8. But I am looking into including WRS1, Sentinel-2, and other sensors as well. It also provides input data information for Python code. So let's just say I want to write some code where I want to process surface reflectance data or thermal data or whatever. This tells that this will go ahead and tell the code where to look for the data, so I don't have to remember where exactly on disk these things are sitting. It will also include other things like projection information, etc., and so on. I also wrote a separate submodule to handle the input and output data. I really like the NV format, and the reason why is because the NV format is basically two files. One is the data itself, and then the other is the metadata. This includes bands, including number of bands, lines, rows, etc. But it also includes all the information that you would want, like if it's a classifications, if it's spectral data, values, etc., and so on and so forth. You can actually input whatever metadata you want in there on a custom basis. So a lot of different software packages have actually adopted this as their standard instead of, say, GeoTIFF or something else. It has routines for writing the image data itself, header data, and color files. Also included is a geo package, a separate geo package, which has layers for approximate Landsat WRS1, WRS2 paths, and row locations over Ireland, and Sentinel-2 tiles. The Sentinel-2 tiles are an MGRS, which is based off of UTM. The polygons themselves are in ITM, and they're used to test scene location accuracy. Because one of the things I discovered with that previous issue where scenes may be misprojected, I went ahead and said, okay, well, after we're going to go ahead and do the conversion from, after we do the conversion from UTM to ITM, let's go ahead and make sure that this is actually where it should be located. So it just goes and makes sure that the scene center is within 50 kilometers of where the scene center should be according to the WRS2 locations. Now, I also wrote a set of tools known as IEO tools. Those actually do most of the work that needs to be done for the library maintenance, and it's in a separate directory. So basically, it's done in there are basically 4 different scripts that need to be run in order. Actually, there are more scripts, but these were the ones that were written for IEO tools. Specifically, update Landsat, which creates and updates the local scene database, whatever it can grab from the USGS. Then make SPA list. What that does is that goes through, figures out, once you give it a set of parameters, it says, okay, like I want all the data that have 30% cloud cover or less, between such and such dates. So you can restrict the dates, you can restrict even the area you want. Then there's then after you've uploaded and processed the scene, after ESPA's had processed the scenes you want and downloaded them, and I recommend using the USGS ESPA bulk downloader for those data. There's then a script to import these scenes, and then lastly, there's one that goes ahead, takes whatever tiles have been saved to disk. It just goes through and it creates VRTs just to make things easier, because you end up with dozens of tiles. Sometimes you can end up with a few dozen tiles, and going ahead and and loading them all in and whatever can be a bit of a pain. So moving on, I also made it so that it can easily support other projections. Well, maybe not so easy, but it's a relatively straightforward process to go ahead and modify IEO so that it doesn't support Ireland, but instead can support something else, like, for example, the U.S. state of Maryland. In this case, the projection would be Maryland State Plane, NAT 83. As you can see, I generated a set of tiles for it, also identified the Sentinel tiles and the WRS1 and WRS2 areas. And as you can see, Maryland's kind of a weird-shaped state, so it shows that it can work also in situations where your data may need to be saved, and some sort of you may need to actually remove a lot of data for if you're just interested in, say, a state level map of Maryland. Now modifying it is relatively basically you have to follow a series of steps. One is you have to modify the IEO geopackage layers to suit the area of interest, and that you can do in most GIS programs, either ArcGIS or you can certainly do it in QGIS. IEO settings are also determined currently in a config IEO file, INI file. So the projections are set using EPSG codes. The geopackage layers are also determined within, so you can go ahead and modify them. And it's a little bit of it's a little bit of typing and whatever, but it can be done relatively easily enough. Now, installing and running it is a little bit of an issue. I'm not the world's greatest programmer, and I found that while I can get it to compile and create an egg and install it in where it should be in there, it, for whatever reason, at least a version of Python that I use, which is Anaconda, can't see the IEO directory. Earlier versions, there was no problem, but then I don't know what I did, and next thing I know, it's not working, and I can't seem to find the source of the bug. So I did devise a workaround in the IEO tools scripts. Basically, if it doesn't find the IEO tools, then it asks you where to look for it, and then you can just go ahead and point it towards your. If you downloaded it locally, you basically like if you use GitHub, so go to your GitHub directory where the IEO would be located, and it finds it, and then it works. And part of the other issue is that the IEO INI file gets bound up in the egg, so if you decide suddenly that you need to make some changes or whatever, it's not very accessible. And so I'm wondering, would it be a good idea? Do I go ahead and say create an environment variable for either Windows or Linux, and then that would go ahead, tell it where to look for the INI, and then you could go ahead and modify there in a much easier manner. And then it would probably also make install a bit more straightforward. The other issues, geopackages do have their own limitations. Apparently, they are based off of SQLite, which apparently isn't network friendly. I haven't tested this over the network, but I was reading on something about geopackages because I'm still kind of a newbie when it comes to them. And so running into bugs here and there, and then suddenly somebody's like, "Oh yeah, don't use them over the network because they're not designed to do that." The other thing is it can't really work against PostGIS or other spatial databases. It's supposed to just I'm not really a database person, so for me the simpler the better. But I'm sure that there are much better ways to do things in the way that I do it. The other thing I discovered is, and this is probably not something I can do much about beyond adding in some proper processing, is that some Landsat 7 scene footprints are incorrect. They'll show the full extent of what you'll be getting from the USGS, but that includes a lot of no data, a lot of pixels that aren't actually data there. It's just stuff that you'll get, which will have a value of -9999, and stuff that you basically would be wanting to get rid of anyway. So rather than the actual footprint of what was acquired from the satellite. So the future plans here include unifying IO tools and IO into a single module. I want to incorporate some external code, specifically the USGS bulk downloaders, so you don't have to download them separately. Also use the USGS ESPA API, which will actually allow for, if you want to go ahead and do the ESPA proc list, instead it would go ahead, it would identify what you want, and then it would automatically contact ESPA, transmit those data there. It could even go ahead and check as things are going on, and then automatically download too. And then the other thing is somebody went and wrote a module called SentinelSat, which can be used to search and download data from the Sentinel archives. And I'd like to bring that in too, because if somebody else has written something, it saves me a lot of time having to go ahead and write it myself. And then create the importation functions for Sentinel data, prepare for Landsat Collection 2, which is coming up soon. Right now it's Landsat Collection 1, so hopefully Landsat Collection 2 is going to be a minor change in terms of just adding in some things here and there. Getting it from what they had before Collection 1 to Sentinel 1 was, to Collection 1 Landsat was a real pain, because they moved from an XML-based set of metadata to JSON. Other things, create a tiling system that's appropriate for marine applications. Like I said, my applications are land-based, but there are plenty of people who use remote sensing imagery for looking at the oceans, particularly at the higher spectral resolution, and this is not appropriate for what we're doing. So I need to, if anybody here happens to do marine mapping and can give me some information on what their requirements are, that would be great. I also would like to bring in other things like EO on Hyperion and ALI, which was a satellite that was flying up until about 2 or 3 years ago. And there are some historical data that would be very useful to bring in. Venus, which is a French-Israeli satellite, which is acquiring data for 4 locations over Ireland. And other sensors also bring in DEM data, whether it's Aster, whether it's the USGS, whether it's SRTM. I want this to be a collaborative project that suits the needs of the Irish and the broader EO and GIS communities. And you can go ahead, access the code there.